To progress to the next level in understanding reality, we need to combine quantum mechanics with Einstein's general relativity. And to do that, most physicists believe we need a theory of quantum gravity, which means we need gravitons. But it also seems like the laws of physics make it impossible to ever detect this quantum particle of gravity. Almost like the universe is set up to keep the final answer forever out of our reach. So, can we outsmart the universe, catch a graviton, and finally, solve physics? In 2012, the legendary physicist Freeman Dyson gave a talk in which he speculated on the possibility of ever detecting gravitons. He was not optimistic. In his Poincaré Prize lecture, he laid out how the universe seems to conspire to make the detection of the quantum particle of gravity impossible. In some cases, it seems to be impossible for all practical experiments. The experiments are just too outlandish to ever happen. But in other cases, graviton detection seems to be in principle and fundamentally impossible. We're thwarted by the appearance of black holes or by the quantum vacuum from ever glimpsing a graviton. So, does the universe really prohibit us from ever seeing the building block of the fabric of space-time? As a reminder, the graviton is the quantum particle of gravity, just as the photon is the quanta of electromagnetism, gluons of the strong force, etc. But the graviton is more than that. It's the building block of the fabric of the universe. In the same way as an electromagnetic field can be thought of as being made of a sea of virtual photons, space-time is made of gravitons. At least that's true if space-time has a quantum nature, as most physicists seem to believe. All theories of quantum gravity require them, from string theory to loop quantum gravity, so it's probably worth trying to spot one if we ever want to verify these theories. Now, in the past, we've talked about indirect ways to test the quantum nature of gravity, but what about detecting the graviton itself? Well, there are two broad ways we can think about graviton detection. On the one hand, we can take what we know about detecting classical gravitational fields and try to apply it to a quantized field of gravitons, basically to detect the gravitational effect of a single graviton. On the other hand, we can treat gravitons like every other particle and use the same techniques we once used to, say, squeeze photons out from the electromagnetic field. By tackling both perspectives, we can get a reasonably comprehensive sense of how impossible graviton detection may really be. So let's start by trying to detect the gravitational effect of a single graviton. We'll think about this in terms of the most sensitive gravity detectors ever built, the Laser Interferometer Gravitational Wave Observatory, LIGO. This pair of detectors tracks the subtle differences in phase of a pair of laser beams travelling along 4-kilometre perpendicular arms. When those phases fail to line up, it indicates a relative change in the lengths of those arms, a possible signature of a passing gravitational wave. We've used these observations to spot gravitational waves from hundreds of merging black holes and neutron stars since the first detection in 2015. So what would it take for a laser interferometer along these lines to detect a single graviton? We'll follow Dyson's argument here. LIGO is able to detect gravitational waves with a strain of 10 to the power of minus 22. That's the relative change in length that the device is sensitive to. It corresponds to 1/1000th of the width of a proton for the 300 back and forth reflections along LIGO's 4-kilometre arms. If gravity is indeed quantum, then gravitational waves are made of a coherent superposition of gravitons, in the same way that our lasers are made of photons. A wave at LIGO's strain limit would contain at least 10 to the power of 36 gravitons. We're trying to see a single graviton, so in principle, we'd need a detector that's 10 to the power of 36 times more sensitive. The critical question we need to ask is, how precisely do we need to measure the variation in the length of detector arms to pick up that single graviton event? It turns out that the answer is sort of independent of the type of gravitational wave. For optimal sensitivity, we need to be able to measure a length difference of the order a single Planck length. This should already raise concerns, because the Planck length is the distance where our current understanding of space breaks down. But let's proceed. The limits of measurability of literally everything is defined by the Heisenberg uncertainty principle. The principle sets an absolute limit on how precisely we can know complementary pairs of properties simultaneously. For example, the position or momentum of something. Let's start simple by imagining one LIGO arm as a pair of free-floating mirrors. A gravitational wave causes the distance between them to change, and we want to measure that changing distance. That's effectively measured by bouncing a photon between them. However, that photon also imparts momentum on the mirrors, inducing an uncertainty in the mirror position. The more precisely we want to measure those positions, the higher the frequency of light we need, therefore the more momentum we have to impart. The position-momentum uncertainty relation can be used to relate the limit of the position measurement to the imparted mirror momentum. We can then convert this relationship to one involving time. So in order to accurately measure the separation of the mirrors, that measurement has to happen fast, faster than the mirrors move out of position due to the act of measuring. Long story short, we can maximize the precision of our measurement of the mirror separation in two ways. By reducing the distance between the mirrors, that reduces the measurement time, and by increasing the mass of the mirrors. Heavy mirrors move more slowly when bumped by the measuring photon. If we want a 1 Planck length position precision due to the passage of a graviton, the mirrors need to be massive enough and close enough together that they form a black hole. Well, that sucks. By definition, the formation of an event horizon prevents our distance measurement. Dyson shows that we get the same issue via a different argument even if we fix the mirrors in place. In general, any distance measurement on the scale of the Planck length gives us black holes, which means that the direct measurement of the effect of a single graviton by a LIGO-like device is fundamentally impossible. Okay, let's try something else. The gravitational wave approach tries to measure the actual gravitational effect of a single graviton. But maybe treating gravitons gravitationally is using a classical hammer to crack a quantum nut. Instead, maybe we should look for gravitons by the same method we look for other quantum particles. We can summarize that method in very general terms. Crash particles together and see what happens. The physics of colliding particles is inherently different to the interactions of classical waves, so maybe that's the right approach for spotting a particle that arises from a quantum field. The most obvious example of the particle collision method is, surprise, surprise, a particle collider. We discovered the Higgs boson by building a collider so large that its collision energies could generate the massive Higgs particle. And that collider is the 27-kilometer diameter Large Hadron Collider. So how large a collider do we need to generate a graviton? Well, gravitons are massless, so the energy isn't needed to give them mass like it is with the Higgs. Rather, energy is needed to increase the chance of generating one. Gravity is the weakest force by a long, long way. It's 24 orders of magnitude weaker than the weakest of the other fundamental forces. A fact which itself is a conundrum called the hierarchy problem, which obviously we've talked about before. In quantum terms, that weakness can be expressed as a very small coupling constant between the graviton and the other particles. The probability of generating a graviton in a particle collision depends on that coupling constant. And despite the word constant, the coupling factor actually increases with the energy of the interaction. At around 1 billion joules, the coupling for gravity reaches the ballpark strength of the other forces. So that's the energy that we need to reach in our collisions to have a fair chance of producing gravitons. And how big an accelerator do we need to reach 1 billion joules? Well, the LHC collisions reach a whopping millionth of 1 joule. Now, for a fixed magnetic field strength, collision energy scales directly with collider size. To get to the energy needed to generate a graviton, a collider with the same magnets as the 27-kilometer LHC would need to be around 3 light years in diameter. much bigger than our solar system. That sounds insanely difficult, but it's in principle possible. And once we built this graviton factory, we then get to the real challenge. It's not creating gravitons, but actually detecting them. Now, massless gravitons are stable, so we can't rely on looking for their decay products. We need to see one via its gravitational effect, which we just saw may be impossible, or when it's absorbed by or scatters another particle. So the OG example of discovering a particle this way is the photoelectric effect, in which an electron is ejected from a conducting plate by a single photon. Einstein used this effect to demonstrate the existence of photons as quanta of the electromagnetic field. So, can we use a similar test to detect gravitons? An equivalent gravitoelectric effect? Well, in principle, yes. A sufficiently high-frequency graviton will carry enough energy to kick an electron out of an atom or out of a conducting plate. We could also imagine a graviton equivalent of the Compton effect, in which electrons are ejected from atomic orbitals. Either way, we shift the problem from detecting gravitons to detecting electrons, which is pretty easy. Now, the probability of an electron absorbing a graviton to produce one of these phenomena depends, again, on the coupling strength of gravity. So, just as with graviton creation, this phenomenon is super unlikely. Another way to think about this interaction strength is in terms of a cross-section. It's called a cross-section because it tells us how big an electron looks, say, to a graviton. How close the graviton needs to get to the electron's center in order to hit it and get absorbed. And for the graviton-electron interaction, the cross-section is proportional to the square of the Planck length. So even if we can create a graviton in our interstellar-sized collider, let's call it the SLC, Stupidly Large Collider, we can probably never actually detect it. The other way we can increase the likelihood of a gravito-electric interaction is by increasing the number of gravitons in the right frequency range. So maybe we amp up the power of our SLC, or maybe we find a natural source of gravitons. The theoretical physicist Steven Weinberg calculated that there are potentially a huge quantity of high-frequency gravitons being emitted by the Sun. These are produced by electron-graviton interactions in the hot, dense core of the Sun. At the energy that we need, the Sun should produce about 10 to the power of 24 gravitons per second. This amounts to about 4 per square meter per second passing through the Earth's surface. You probably didn't notice the several that passed through you during just this sentence. The interaction cross-section for this is so small that these solar gravitons only interact with a particle of matter roughly once every billion years or so across the entire volume of the Earth. Now, we could build, say, a planet or even a star-sized detector and maybe get a detection every 1,000 years rather than every billion, but that still feels like an unsatisfying yield. We probably need actually a stronger source of gravitons than a mere entire star. The best option might be the collapsed core of a dead star. Robert Gould estimates that a hot white dwarf or a neutron star would emit, respectively, 100 and 100,000 times more gravitons than the Sun, although over a shorter timescale. So placing a star-sized detector near such a stellar remnant, many light years away, might get us a single graviton on a human timescale. Of course, the path to building such an experiment is far beyond human timescales, if it's possible at all. And if we were to somehow pull this off, we'd face an even more basic issue. Neutrinos. These ghostly particles are notoriously hard to spot. Most of the Sun's neutrinos pass straight through the Earth, and we've built detectors out of the Antarctic ice cap to catch the occasional rare interaction. But by comparison to the shy graviton, the neutrino is a party animal. For any of our graviton sources, regardless of whether it's our Sun, the white dwarf, the neutron star, our detector will interact with 10 to the power of 34 neutrinos per single graviton. And distinguishing that graviton from the neutrino noise seems practically impossible. Let's try one more method that on the surface looks promising. In the 1960s, Mikhail Gertzenstein showed that electromagnetic and gravitational waves in a strong magnetic field can couple together. This is more promising than looking for interactions between gravitons and, say, electrons. EM and gravitational waves, which both travel at the speed of light, can experience wave resonance that allows energy to transfer between them at a much lower coupling strength than is needed for the absorption of a graviton by matter. This means a photon may be transformed into a graviton and vice versa. So, if we shoot a graviton through a magnetic field, it will oscillate between graviton states and photon states. This is called the Gertzenstein effect. Now, to do this, we need a long hollow tube threaded by a strong magnetic field pointed towards a source of gravitons. The hope is that some of those gravitons will turn into photons that we can detect. And as you may have guessed, the universe again conspires against us. The magnetic field needs to be quite strong for the Gertzenstein effect to work. How strong? Well, strong enough that we have spontaneous creation of matter-antimatter pairs inside the tube. The vacuum polarization resulting from this limits the coherence of EM waves in the tube, preventing resonance with gravitational waves and shutting down the Gertzenstein effect. So we are at strike 3 for detecting gravitons. It seemed that the universe really doesn't want us to see its deeper structure. But is it really impossible, or just nearly impossible? In a couple of the cases we looked at, the answer is that it's impossible. The barrier to graviton detection seems fundamental. The formation of black holes, the breakdown of the vacuum, tells us that the laws of physics forbid graviton detection by these methods. But in other cases, it's just astonishingly difficult. We need star-sized graviton sources and detectors, and some yet unknown way to filter neutrinos. But next to impossible is still possible. I'm saying there's a chance. And maybe the problem is actually just that we haven't come up with a smart enough experiment yet. Or maybe we have. Since Dyson's 2012 lecture, we've detected gravitational waves directly, and we've made major advancements in quantum technology. This has inspired a new generation of physicists to come up with a new generation of proposals. For example, we may be able to combine the two broad approaches that I mentioned, using a LIGO-like interferometer combined with absorption of gravitons, this time by a detector with novel quantum properties. How does that work? Well, that's for an episode coming soon, when we'll find out how we really may be able to detect the particle at the heart of space-time.